In this class, we will discuss about numerical integration. And in this numerical integration section, we will be discussing about two different methods. One is trapezoidal rule or trapezoid rule, and second one is Simpsons rule. Okay. So first, we will consider the trapezoid rule. We can call it as trapezoidal rule. Okay, for numerical integration. So if you have given any function f of x, how we can integrate that function numerically? That is what we are going to do here. So the theory is like this: the process of evaluating a definite integral from a set of tabulated values, which is called as which is the numerical integration technique. Okay, so first we have to evaluate. This process is nothing but evaluating a definite integral, okay, from a set of tabulated value. Okay, from a set of tabulated value, and that values of integral. So this process is called as the numerical integration. So if you, it can be defined like this: if you are having integral like this, I equal to integral a to b. A is the lower limit and b is the upper limit, and f of x is the function dx. Okay, so this is the general definition for the integration. Okay, definite integral, you are having some definite integral from which is having lower limit a and upper limit b. So we can write it as integral a to b f of x dx, which will be equal to a to b integral a to b f instead of f of x, I have written y dx. So where y is nothing but f of x. Okay. So this y can take values y0, y1, y2, y3, etc. up to yn for different values of x, like x0, x1, x2, x3, etc. up to x. So for x0, we are having y0, this y value which is equal to y0. For x1, we are having y which is equal to y1, and so on. Okay, so for different x values, we are having different y values. So we will get a set of data. Okay. So basically, we are having a function, and from that function, we are considering a set of tabulated values for each and every x points that we consider. Correspondingly, we'll have a set of y values, right? So we will tabulate all those values, and from that tabulated values, we will find out what is the integration, integral result of that particular function. Okay, so basically, we will consider the function like this. So the process is like this. If you are considering this as your y-axis, this is your y-axis, and this is your x-axis, and you are having some function like this. So this is your f of x function that is equal to y equal to f of x, and this is your x-axis. So if you are having, if you are considering any x value here, any x value on this x-axis, correspondingly, you will be having a y value. You will be having y value. So this is your x0, and correspondingly, you will be having y0 here. And this is your x1, you will be having y1. This is x2, you'll be having y2, and so on, etc. If you consider, if you are considering it is not continuous here, then you can consider it as etc. So many such points, okay, etc. And then this is our some x value, and this is xn. Let's consider this is the last one. So this curve is up to this. Okay, so that is the last point. So that is xn. This one will be xn minus 1, and so on. So that is the picture. And if you consider this kind of a curve, so we are considering different y values for different x values, and we are tabulating all those values, and how we can do the integration with this tabulated values. Okay. So instead of integrating that function directly, how we can integrate that particular function with this tabulated value. So this kind of integration is useful when you don't have any definite integral result. Okay, if you don't know the any definite integral result for this integration, then it will be very much useful. For example, if you are having very complicated function to integrate, from A to B, and it is very difficult to integrate analytically, then in such cases you can use these numerical methods to integrate that particular function, and you will get easily almost approximated result for that particular function, okay, within that range. Okay, so that is how it is going to be useful in real situation. So this is the scenario, and if you consider the difference between these 2 points, these two, so you can see here this is x0. Okay, this is x0. This x0 is nothing but your a, limit a, if you are integrating this function, and this xn, this will be your b, the final point of x. So you'll be integrating from a to b, lower limit to the upper limit. So xn will be equal to b and a will be equal to x0. That's what we have written here. X0 will be equal to a, and you can see your xn, that is equal to b. Xn will be equal to b. And what is xn? Xn will be equal to x0 plus nh. Why? Because if you consider x1, what is x1? X1 is x0 plus this h. If you consider the separation between these 2 points, x values, that is h, then this x1 will be equal to x0 plus h, right? And if you consider x2, x2 will be equal to this x0 plus 2h, 2 times h. If you are considering these two, we are considering here the separation x separations or period um, which is equal. Okay, so we will consider here equal intervals. So this is nothing but equal intervals. Equal intervals, which means that h value is constant for all these intervals. So we are considering the interval which is h. Okay, so x2 will be equal to x0 plus 2h. X3, if you consider that, it will be x0 plus 3h, right? So similarly, if you write for xn, so xn will be equal to x0 plus nh. That's what we have written here, and that is equal to b. That is the final x value. So up to that, we have to integrate. So again, you consider the same equation here. So we are considering the initial point x0 and final point xn. That is your limit y dx. That will be equal to what is this? This will be equal to. I'm just replacing this y with f of x, and f of x, in f of x I'm replacing x with x0 plus, let's consider this as nh, x0 plus nh. So that will give me my dx. So I should write dx will be equal to, if you are differentiating this one with respect to n, so we'll get dx by dn equal to h. So this is h dn, right? H dn, h times dn, that will be dx. So if I am writing x equal to x0 plus nh, so x is any point in the x-axis, any of the x values. So it depends on n, that will be different. Okay, so depending on n, this x value will be different. So for example, if you consider the third x value, so that will be x, x3. Okay, third x value, that will be equal to x0, x0, x1, x2. So this is fourth x value, right? So fourth x value, that is x3, that will be equal to x0 plus 3h, right? So this can be any x. So any x can be x equal to x0 plus n, depending on that n value. So if I replace that x with x0 plus nh, so I will write this as n. So I have used p because we have used p for the Newton's forward method, I think. So okay, for interpolation we have used. Yeah, this interpolation formula we are using p. That's why it is coming p there. So I have to replace all the p's with n. So here also I can write this is n. Okay. So if I replace x with x0 plus nh, x with x0 plus nh, then I can say I can replace this y dx with f of x0 plus nh dn, and h I can take outside. That is h dn is equal to dx. So this dx will be replaced with h dn. Okay, so that h is coming outside, and here we are having dn. Okay. Now considering this Newton's forward interpolation formula, you can see here. So in this interpolation formula, we can see h, this if you are substituting that in this particular uh, for this f of x 0 plus nh value, so then you can get this kind of equation. You know this Newton's interpolation formula y0 plus, instead of p I can write n delta y0 plus, then n times n minus 1 del square y0, and sorry, delta square y0, then n times n minus 1 times n minus 2 times del, delta cube by 0 by 3 factorial, all those things. So this we already discussed, plus etc. So up times dn. Okay, so this is what we are going to do. Okay, so this is nothing but the interpolation equation, Newton's forward interpolation formula. So in that equation, we have to use this equation to do this integration. So instead of f of x, I am just substituting this particular Newton's interpolation formula. So which means that I will get any value of y in this by using this particular formula. Okay, so just we have to substitute the n value, and we'll get the corresponding uh, y value. Okay, so this is just for that, and I am substituting f of x equal to that this from Newton's interpolation formula. And now if you reduce that on simplification, so what you had to do, this is y0. So when you are integrating y0 with respect to dn here, you will get n y0, right? Similarly, when you are considering the second term, then we will be having n times delta y0, which means if you are integrating this n, then you will get n square by 2 delta y0. Then this one is n square minus 1 divided by, sorry, minus n by 2 factorial, that is 2. So if you integrate this term with the dn, so this will come as n cube by 6, because 3 will come in this denominator. 3 into 2 is 6, minus this will become n square by 2. 2 into 2 is 4, right? So in this way you have to integrate all these terms, and from that we will get equation. This equation will become like this. You are taking one n outside, n times h times y0. Okay, that's okay, because first term will be n y0, second term is n square by 2 delta y0, that you can get from here. Just integrating this n square by 2. So if you integrate this one, this will give n square by 2 delta y0. Okay, first term will be n times y0, and in that one n I took outside. See that here, and n into n by 2. So this is n square by 2 delta y0, and third term is n into 2n minus 3 by 12. So if you simplify this, you can directly get this is nothing but n cube by 6 minus n square by 4. If you simplify, this is, you can do that. So this is 2 times n cube, okay, minus this one is 3 times n, right? 3 times n square. This n also you have to consider. Okay, so 3 times n square, then divided by 12. So this you can write this 12 and this 2 get cancelled. So we'll get n cube by 6 minus this 3 and this 2 will get cancelled. So this will be n square by 4. So we'll get same result as we discussed here. Okay, so that is same. So if you simplify that equation, you will get an expression like this for integration x0 to xn y dx will be like this. And fourth term also you can consider. Okay, and this particular equation is known as Newton's quadrature formula. Quad, CODE, quadrature formula. And in this quadrature formula, general formula, we can substitute n equal to different values, n equal to 1, 2, 3, etc. And with those n values, we will get different quadrature rule, which means that we will get different rules for definite integration of or approximation of the definite integration. Okay, which means numerically we have to calculate those integration. Okay, so this quadrature rule is nothing but the approximation of those definite integral. And for n equal to, if you substitute n equal to 1 in this general Newton quadrature formula, then we'll get trapezoidal rule. Okay, and if you substitute n equal to 2, then we'll get Simpsons rule and so on. So we first will consider this trapezoidal rule. Trapezoidal rule we already discussed, which is for n equal to 1 in this general equation. So putting n equal to 1 in this Newton's quadrature formula, and so if you substitute n equal to 1, then the first terms, if you look at this, you can directly look into this equation so that you will understand that. So if you substitute n equal to 1 here in this equation, for example, for this first integration equation, so you can see this. So if you substitute n equal to 1 here, n equal to 1, what will happen for n equal to 1? So for n equal to 1, so this all p's are n, and so this all these are n now. So if you are considering n equal to 1, then this term will become 0, right? This term also will become 0, n minus 1 is there. So all the higher order terms, all these terms will become 0, except these two terms. So only these two terms exist when n equal to 1, because in all other terms n minus 1 is there. Okay, so in when n equal to 1, all other terms will become 0 except the first term delta y0 will exist. So all other terms will become 0. Okay, and so that we can write integral x0 to xn, x0 to x1. For example, we are integrating from the first x value to the next x value, that is x0 to x1 y dx. In that case, we will get h into y0 plus half delta y0 from that equation. Okay, so this is nothing but h into y0 plus half delta y0. That is the integration formula. So that you can get from here also. And you're substituting n equal to 1, then you will get the same expression. So or you can directly take it from the previous example. I mean the first one. Okay. So this is h into y0 plus half into delta y0. So what will happen to this particular case? In this case, what will happen? So delta y0, what is delta y0? Delta y0 is nothing but, in this case, I'm talking about this case, that is we are varying from x0 to x1. So delta y0 will be, that is y1 minus y0, right? Change in this y1 and y0. That we already did for the interpolation techniques. So we have y1, y0 here, y1 here, y2 here, and so on. So this will be your delta y0, delta y0 value. So y1 minus y0. So y1 minus y0 is delta y0. If you substitute that in here, then we will get half times y1 minus y0. So this will become half times y1 minus y0, this delta y0 term, y1 minus y0. So if you subtract that, y0 is here plus y0 minus half y0 is here, so that will become half y0, and we are having half y1, so that will become y0 by half and y1 by half. So in general, it is h by 2, 1 by 2 I take outside, and y0 plus y1. That is the equation for integral x0 to x1 y dx. Now, if similarly, if you consider integral x1 to x2 y dx, you will get h by 2 y1 plus y2. So here it is a y0 plus y1. Here it is y1 plus y2 when you are considering x1 to x2. Similarly, if you consider for n x values, then you can, in general, you can write, in general, you can write xn minus 1 to xn y dx. Integral xn minus 1 to xn y dx will be equal to h by 2 times yn minus 1 plus yn. That is in general. Okay, so if you take all those values, add all those values, okay, so what you are doing, you are considering that curve, you are making these intervals, different intervals like this. Okay, so what is the this is your x-axis, this is your y-axis over here, and what is this? This is x0, this is x1, x2, etc. up to xn. Okay, so what you are doing, you are considering this integration between these two, x0 and x1. Then you are considering integration between these two, then integration between these two. So if you are taking integration between x0 and x1, then that will be the area of under this curve, right? And if you are taking integration between x1 and x2, okay, then that will give you area under this curve. So if you are adding all those integrations between these limits, like, the nearest limits, then you will get the complete area under this curve. Okay, so then I can write from x0 to xn, integral x0 to xn y dx will be equal to adding all those values, all those areas, which means h by 2 y0 plus yn, y0 plus yn plus 2 times yn plus y2 plus y3 plus etc. up to yn minus 1. So this will be 2 times of the summation of all those values y1, y2, y3 etc. up to yn minus 1, and this 2 will be only 1 times the y1 and yn. Why? Because when you are considering this, you can see that here when you are considering this, you are having only one y0. Here you are having y1 h by 2 times y1, and here also you are having h by 2 times y1. So in this 2 integration, 2 times h by 2 y1 will come. Okay, so 2 y1 terms are there. Similarly, if you consider y2 also, it will be 2 times. Y3 also will be 2 times, and up to yn. Yn will be only 1 time. H by 2 times y. So I will take h by 2 times yn and y0, which is coming as only 1 time in this equation. So h by 2 times y0 plus yn I will take at 1 time, and plus 2 times y1 plus y2 plus y3 plus etc. to yn minus 1. That is equation for the trapezoidal integration. So you don't have to consider these dots between. Consider this as y0 plus y1 by h by 2 y0 plus y1 plus 2 times y1 plus all other terms plus etc. up to yn minus 1, not yn, up to yn minus 1. So now consider that particular equation. That particular equation will give you the trapezoidal rule. That is the trapezoidal rule or trapezoid rule. Okay, so this sentence, this paragraph, I have already explained what is happening in that particular case, why we are taking like this. So it will give you the entire area under the curve. That is nothing but the integration of that particular function over that entire range. Now let us consider Simpson's 1/3 rule. So in Simpson's 1/3 rule, just put n equal to 2 in your equation, n equal to 2 in this Newton's quadrature formula, and that will give you equation like this. As we discussed earlier, just put n equal to 2 in that particular equation, then that will give you x0 to x2. If you are going from x0 to x2, why it is going from x0 to x2? Because you are considering n equal to 2. So first you are considering x0, then it will take 2 steps. So the next x value, that will be x0 plus nh. So which means x0 plus 2h. This is nothing but x2, right? So from x0 it will go to x2. So when you are considering n equal to 2, that is the case for Simpson's 1/3 rule. So it will go from x0 to x2 for the first case. That will give you, and if you substitute that n equal to 2, then you will get 2h times y0 plus delta y0 plus 1 by 6 times delta square y0. So this is the equation. And from that, if you substitute delta y0 as y1 minus y0 and take this also delta square y0. So for that case, we have to consider these two terms, delta y1 minus delta y0. In that case, we have to consider and substitute again these two terms in that equation. And if you simplify that, you will get h by 3 times y0 plus 4y1 plus y2. That will be the equation for integration of x0 to, from x0 to x2 y dx. Further, if you consider x2 to x4, next you have to consider from x2 to x4. There is no x3 or x1. Okay, so once you have reached here, then you have to consider x2. From x2 you have to go 2 steps, right? So that will be x2 plus nh. So that is 2h. Again, you have to go to 2h times. So this will be x4. From x2 to 2h steps, then it will give you x4, fourth x value, fifth x value. Okay. So that will be x2. Next integration will be from x2 to x4 because your n equal to 2 here for Simpsons rule. So x2 to x4 y dx, that will give you h by 3 times y2 plus 4y3 plus y4. Remember, here it is for y1, here it is for y3, here it is y2, y4, that is your limit x2, x4. Here the limit is x0 to x2, so we are having y0 and y2 here. And in between you are having 4y1, the y value in between these two. And here also y2 and y2 plus 4y1 you can see here, and 4 times plus 4 times y3, y value in between these two, 4 times that. So in similar way, if you consider for the nth term, you will be getting xn minus 2 to xn. Last term, you have to consider like this. So this is xn minus 2 to xn y dx. If you consider, then you have that is equal to, in general, you can write h by 3. Here you can see 1 by 3. That's why it is called as 1/3 rule. So you have h by 3 times yn minus 2, yn minus 2 plus 4 times yn minus 1 plus yn. So this is the general formula. Okay. So if you are considering all those terms, now you are considering all those terms from x0 to x2, x2 to x4, x4 to x6, all those terms up to xn, adding all those integration, then you will get the complete integration of that particular function over x0 to xn, right? So I can write it as x0 to xn, x0 to xn y dx, which will be equal to h by 3 times y0 plus yn, because y0 and yn will come only once. You can see we are having only one yn here. Similarly, we'll be having only one y0 at the first equation. Okay. For all other terms, you can see this is 4 times yn minus 1. What is this n minus 1? All this n minus 1 will be odd terms. You can observe that. You can observe that in the previous equations also. You can see y3 here. Here you can see y1. Okay, so y1, y3, next one will be y5, and so on. So all these terms are, this term with multiplication of 4, that are the odd terms of y. Okay, so that is, we can consider it as 4 times. So in that case, we can write it as 4 times y1 plus y3 plus y5 plus etc. up to yn minus 1. So that is this term. Plus, what is 2 times? 2 times this term. Okay, why it is 2 times? because you are getting it two times in every equation. In each equation, you can see this is y0. So this one is y0. This is only, this will appear only one time, but this one is y2. Okay, and this one also y2. So you are having y2 here, and you are having y2 here also. So you are having two times y2 in your integration. Two y2 terms are there. Similarly, if you consider y4 also, if you consider y4 here, next integration after this one, next integration will be from x4 to x6, right? So in that case, y dx, you will be getting h by 3, h by 3 times, then you will be getting, instead of this y2, you will be getting y4. So you'll be getting y4 in this integration as well as in this equation. So you'll get 2 times y4. So 2 times y2, 2 times y4, 2 times y6, 2 times y8. So in general, we can write it as like this. It is 2 times y2, y4, y3, y6, and so on, yn minus 2. Yn we already taken here, y0 also we have taken here. So it is y0 plus yn plus 4 times odd terms, you can see here, y1, y3, y5, etc. up to yn minus 1, n minus 1, and 2 times y2, y4, y6, etc. up to yn minus 2. Okay, so this is the equation for Simpson's rule. So if you do this one, this equation, by using this equation, if you calculate what is the integration, then that is nothing but the numerical integration with the Simpson's rule. Okay, so substitute what is the y0 value, yn value, y1 value, y3 value, all those values for y, and add all those things and multiply with h by 3, then you will get the integration of that function from x0 to xn numerically. So this equation, this is called as Simpson's 1/3 rule. Okay. Now let us consider a very simple example. So if you are considering, let's say, integral of x 1 to 3, limit is 1 to 3 dx. Let's consider this is a very simple example. So if you do this analytically, then you will get this is nothing but x square by 2 from 1 to 3. So what is this? This is 3 square by 2 minus 1 square by 2. This is nothing but 9 minus 1. 9 minus 1 by 2. So this is 8 by 2 is 4. So this is the integration result that you get when you are using your f of x equal to x4, which is varying from 1 to 3. Limit is from 1 to 3. Okay, so now we will do this same example with the help of program. So in there, I will explain, or I will show you how we can do this in this case also. Here, you just consider this x0. X0 will be your first value, that is the lower limit, that is 1. X0 will be 1. And as you know, x1 will be equal to x0 plus nh. So the next value we have to consider, this is x1, so this is h. So it depends on h value, you will be getting different values. So this will be, let's say 1 plus, if I am taking h as 1, then this will be 1. So the x1 value will be 2. So then x3, what is x3? X3 value will be x0 plus 2h, we can consider. So 1 plus 2 times h is 2, that is 3. So this is nothing but your b, that is the upper limit. So x3. Okay, and correspondingly, you have to calculate what is y. Okay, so y will be, so y0 will be, x0 is 1, so y0 will be 1, right? And y1 will be, just substitute in this equation, what is x value. And y1 will be, x1 is 2, so substitute that x1 in this equation, that is nothing but x. So we'll get x equal to, that is 2. So if you are having x square, then y1 will become 4, right? So y2, this will be equal to, this one is, okay, this is 2, right? This is x2, not x3, it is x2. So this x2 will be equal to 3, that is now in the final limit range, so we cannot go any more x value. So y2 will be equal to, so this is 3, right? It's 3. Okay, I think that is right only. Now you substitute that in your integration equation. What is that? If you are using trapezoidal rule, if you are using trapezoidal rule, what will be that equation? That is 1 by 2 3 and let me put n equal to some 2, you see some change. No, there is not much change happening because we are getting 4 out. It is pretty good, right? Because even if you are taking it set 2, so because it is, maybe it is because of the function is x, but it depends on h value. For different h, we are supposed to get different values here, because you can check that for different functions. Okay, maybe because of this is function x that is giving. I will show you the change with the Simpsons rule. So for that, I will just copy that particular program for Simpsons. Let me copy that one. So in this Simpsons program, these steps are almost similar, but a very small variation is there. So instead of, so this is the Simpsons program. So the same definition of function here, a, b, and all of those things, and h values b minus a by n, all those things are same. Only this part it is going to change. In this part it is going to change. Okay. So if I mod 2 is equal to 0, which means that if the given y value, which is its order is even, okay, if it is even, I mod 2 means if you are dividing this I value with 2, if it is giving you 0 remainder, okay, that is what mean by I mod 2 equal to 0. There is no remainder. Okay, for example, if this I value is 1, then if you take 1 by 2, then there will be some remainder. So it will not go to this step. It will go to this step, else step. It will go directly to this step. So when I equal to 1, it will directly go to this step, so that it will take sum equal to sum plus 4 times f of this one will be x1, right? X equal to a plus ih, that is a plus h, that is x1. So 4 times f of x1 will come here. The next time I will become 2. When it will become 2, you are checking if I mod 2 is equal to 0. Yes, it is 0, because 2 mod 2 is 0. 2 by 2 is giving you 0 remainder. So this is right. So then it will go to this step, so that your sum will become sum plus 2 times f of x. Okay, so which means that 2 times f of x2. Then when I equal to 3, again it will check this condition, it will not be satisfied, and it will go to this step. Again, it will add sum plus 4 times f of x3. So all the odd terms will be added in this line, in this instruction. All the even terms will be added in this instruction, and total of that will be your sum when it exit this for loop. And finally, you will get integral, which is equal to h by 3 times f of a is y0, and f of b, that is also available, that is xn, sorry, yn, plus 2 times this sum, total sum, which you have calculated here. I think that is right. Okay, is there any change? Let me see that. For the case of Simpsons rule, equation will be like, okay, so it is h by 3 times yn, sorry, 4 times y1 plus y3 plus yn. So odd terms will come. Okay, that is right. And 2 times y2 plus all those things will come, right? Yeah, I think this 2 is not required, right? This 2, that 2 is not required. This 2 is not required, I think. Let me see that. Right? Because we are considering the 2 times terms and 4 times terms separately. So I think that is not required. Yeah. So okay, so that is the program. So let me run this one. So first it will ask me what is the lower limit, that is 1. Upper limit is 3. And the intervals, let me put 10. It is, this one also give me 4. Its value is 0.2 and integration is 4. Let me change the number of intervals here. So enter lower limit. Probably this also will give me this. Let me see. Okay, for let us 1 and 3, and let me put it as 2. H is equal to 1. Maybe with some different function you have to check. Okay, so let me put some x. Here I will put some other values, some x cube minus x, some other function. We'll just run it and see what will be the integration from 1 to 10 with an interval of, let's say, some 20. That will give me 2450.25 with h equal to 0.45. I don't know exact value. Let me put that. So this is the value 2450.2. Okay, 2450.25 with the 0.45 as h. Now let me change that interval from 20 to some other value. I don't know what was the limit. 10, 1 and 10, right? And this one is, let me put it as 5. Now you can see change. The h value is now 1.8 and the final answer is 2060. Okay, so the value is changed because my h is different now. In that case, we will not get the smooth curve. That's why it is coming like that. We put it again for 20. Yeah. So basically, we are having a smooth curve like this. Okay. So if your h is very large, then you will be getting something like this. I cannot plot it here, but I hope you understood that. If your h is small, then you will not be getting a very smooth curve for that variation. Okay. So it will be some portion of that curve will be gone. I will just show that by opening by sharing that PPT. So I will just stop this presentation and go to the PPT slide, show that. So what actually happening in that case when you are having large h value, so you are considering. Okay, we'll just go it here. So you'll be considering your curve like this. I'm just roughly drawing that. This is x and this is y, and you will be having some curve like this. So if your h is very large, like this, if you're considering one point at this here, and the next point is here, and next point is here, and last point is somewhere here. This will be somewhere. Okay, something like this. And as you can see, if you are joining these two, you'll be getting something like this. Then if you are joining these two, you'll be getting something like this, something like this. It depends on that curve. So basically, you are not having these areas, area under this curve, this portion that is gone. Area under this one, it is also gone. Okay, so if you are taking h very largely, suppose if your curve is something like this, okay, something like this, if it is going something like this, then you will be missing this much of area. This much of area will be gone. That will not come in your calculation. Only this area that will come. The area that I have shown with the green color, that will come in your numerical integration. Only this area will come, and the red colored area which you will not get. So that you will not get the exact value. Okay, when your h is very large. But when you are, if you are reducing that h and considering each of these points, if you're considering this interval, and if you are, which means that you basically you are reducing h value. If you are increasing the number of intervals, you are reducing the h value. This is your h. So if you are having number of intervals which is larger, in this case n is very large, then your h will be very small. So when your h is small, you will be taking each and every portion of this curve and you will get the entire area. You will not miss any part of the area. So that you will be getting the integral value almost equal to the analytical value. Okay. So I hope you understood this section, and that's all about the Simpsons and Trapezoidal Rule.